In this tutorial video, we'll be going through some of the typical pressure questions that you might find in class and on an exam. So to start off with any sort of question, there are two key ideas. First, you need to define what you know and what you're looking for. And the second part is understanding the relationship between those two variables. So let's take a look at what this question is asking. A sample of nitrogen gas has a volume of 500 centimeters cubed and a pressure of 200 kilopascals. And so with that said, let's identify what we have. So we know we have volume, and I'm going to put I as an initial volume. That's 500 centimeters cubed of initial volume. For pressure, that's my starting pressure. I'll put that as initial. We have 200 kilopascals. Kilopascals is a measurement of pressure. And it is looking like we have pressure again. I can tell that based on the kPa. So that's my pressure after I change this situation, meaning that I've changed the pressure from 200 kilopascal to 100 kilopascals. I want to know what the final volume is. So that is my unknown, which will become my x. Okay, so the first thing I need to do is look at what is the relationship between volume versus pressure. Okay, in other words, if I change the volume, how does that change the pressure? And so I think back to the lab and I think to myself, if I reduce the size of an area that contained a gas, what did that mean about how much force those walls were feeling? Were particles hitting it more often or less often? And the smaller the area where the particles have to move, the more they're going to hit the surfaces. So I know that that relationship is that as my volume goes down, my pressure increases because they just don't have a lot of room to move in, and so they're going to be hitting those walls all the time. And remember that pressure is how much force those walls are feeling, either by how many hits they get or by what speed the particles are that are hitting it. So because of that, I know that it is an inverse relationship, and inverse relationships, if you remember, mean that the variables are on the same side of the equation. So that means my P initial is right next to my V initial. And it makes no difference if you write it VI, PI, or PI, VI. It'll get you the same answer. Now on this side of the equation, so this is what we started with. On this side is what we're going to end with in this case, which means that I have a final pressure and a final volume. So I'm going to now set up this equation to include all the numbers. Here I've more or less replaced the variables with the numbers that I found over here. So I know that I have a pressure of 200 kPi and a volume, initial volume of 500 centimeters cubed, and so forth. So I need to isolate this variable, and I do that by dividing this side by 100 kPi, as well as dividing this side by 100 kilopascals. And my answer works out to be that my final volume is 1,000 centimeters cubed. So what I want to do is take a look at that and see whether or not that seems reasonable. Okay, so what I'm saying right now is for this volume, we have it now being 1,000 centimeters cubed. If I increase the volume by 2, would that decrease the pressure by 2? And that seems totally reasonable, because do you notice how we've made the box twice as big, and as a result of making it twice as big, it should feel half the amount of pressure. So that seems relatively reasonable, and I feel like I can move on from there. So for the second question, this one here is where we now have different variables. We have 100 centimeters cubed of hydrogen gas being collected at 50 degrees Celsius. And then we need to find the volume the gas will occupy at 25 degrees Celsius. Now, one of the things about working with pressure equation is we need to convert our Celsius into Kelvin. So the conversion is relatively easy. 0 degrees is 273 Kelvin. And with that said, that means that if I have 50 degrees, 50 degrees would be 273 Kelvin plus 50. And so that works out to be 323 Kelvin, because I've added these two together, because this is my starting point. So 50 degrees, we're now going to call 323 Kelvin. If I have 25 degrees Celsius, I'm going to take 273 Kelvin plus 25. So I'm always adding the Kelvin plus my number. And this is going to be 298 Kelvin. So that's our first conversion that we need to do. So step one is we need to convert Celsius into Kelvin. Okay. Now, the next thing is, again, identifying what variables we have. So as soon as I see that centimeters cubed, that tells me this is going to be my initial volume. So my initial volume is 10 centimeters cubed, and it looks like I have the starting temperature of 50 degrees Celsius, which we now know is 323 degrees Kelvin. And I, again, am looking for the final volume. So that's my unknown. And I have a final temperature of 298 Kelvin. So again, I need to look at the lab and take a look at the relationship of temperature versus volume. And I ask myself, if I change the temperature by either increasing the temperature or decreasing the temperature, how is that going to affect my volume? And the easiest way for me to think about it is that balloon lab that we did, where I increased the temperature of the gas, and I noticed that the balloon started blowing up. That means that there was more volume in that flask because the particles were moving faster and were able to spread out a lot faster. So that means the relationship is direct, that as I increase the temperature, it seems like the volume increases as well. So in this situation, because I have a direct relationship, that means that I know that I need to make sure that my variables are on opposite sides of the equation. So I'm going to put my initial temperature opposite of my initial volume. So T always has to be opposite V. And so when it comes to doing the final ones, these here, I need to build it so that T is always opposite V. And the way that I'm going to do it is by actually making sure that I have my final volume opposite my final temperature. Okay, one thing that I don't want to do is put my TF on this side and my VF on that side. They would still be opposite, but because we're looking at them in a different way, you want to make sure that you have the final in there. Okay, so again, I'm going to set up the equation. So for this one here, continuing on with this, I can write it also as TIVF and TFVI. Anyhow, what that works out is that I replace the variables with numbers, and my VF value that I will get will be 5 centimeters, cubed. Okay, so let's take a look if that seems reasonable. And in this case, it's probably easier to look at the Celsius, but if I have now half of the temperature that I used to, if it dropped from 50 to 25 degrees, that's half the temperature that I had, would it seem reasonable that I would have half of the volume that I initially had? And the answer is yes, because I know that as I reduce the temperature, the volume will decrease also. So my numbers seem reasonable in this one. So the last question that I'm going to go through is one that requires you to understand what STP is. And STP stands for Standard Temperature and Pressure. And these are recorded values, and I'll include those right now. So, standard temperature and pressure means that you have your temperature being at 273 degrees Kelvin, which is the same thing as 0 degrees Celsius, and that you have a pressure of 1.01 kilopascals. So in this problem, you are given the initial volume of 200 centimeters cubed. You're told that you have the initial temperature of 25 degrees, so we want to convert that into kelvins by just adding 273. And you have a pressure of 90 kilopascals. So the first step that we need to do is identify where it's what the final initial is. So we don't know what the volume is because it's asking what is the volume, so that's our unknown. And as I looked up here for standard pressure, I know that my final temperature is 273 degrees, where my final pressure is 101 kilopascals. All right, so in this situation, we've got three variables, which means that we're going to make pressure the anchor point. All right, so initial pressure. So I ask myself, if I increase the volume of something, will that decrease or increase the pressure? And again, that's that volume versus pressure relationship. And I know if I increase the volume, the pressure will go down. So for that reason, it's on the same side of the equation. I take VI and place it right next to it. Now I'm going to look at the relationship of temperature versus pressure. And that means if I heat up the temperature or cool it down, makes no difference, what's going to happen to the pressure? So if I heat up the gas, and I should say gas, then that means that my pressure is going to go up. So that's going to be on the opposite side. So I know that temperature, my initial temperature, is on the opposite side. And so now I need to build my final to look something similar to this. So I know that if I have pressure, final pressure on the opposite side, PF, over here, I know that I need to make sure that my final temperature is opposite my final pressure and that my final volume is on the same side. So this allows us to rewrite this to look like this. And then Ti. Okay, so now we're going to fill in the blanks, and I'll do that in 1 second. What I've done is now I've replaced the numbers based on this top equation. It makes no difference which equation you use, because remember, when you multiply two numbers, they can be multiplied in any order. So I replaced the pressure with the actual number, the volume, and the final temperature. And when I did my calculations, I got an answer of 163.3 centimeters. So I need to do a check of whether or not that seems reasonable. Well, it looks like in this here, my temperature went down. So if my temperature went down, I would expect my pressure to go down. You notice that my pressure actually went up. But when I look at my volume, do you notice how 163.3 centimeters is a reduction in volume? That would mean that if I have less volume, then I would have more pressure. So in this case, it seems like my volume overpowered the change in temperature. And so for that reason, this seems like a completely realistic number.